But U.S. troops are still getting their full paychecks today on day 15 of the shutdown after the president ordered the Pentagon to redirect funds.
The emergency broadcast interrupted every television channel across Florida at 6:47 p.m. on a humid Tuesday evening in April 2025. Governor's voice was steady, but couldn't hide the underlying tension as he announced what seemed impossible: immediate closure of major sections of Florida's coastline, including Miami Beach, Fort Lauderdale, and stretches of the Gulf Coast extending from Tampa to Naples. Beaches were being evacuated. Marine traffic was being rerouted. Coastal residents within a quarter-mile of the shore were being advised to prepare for potential evacuation. The reason, he explained, was an unprecedented geological discovery that threatened not just beachfront property, but potentially the structural integrity of Florida's entire southeastern coastline. Marine researchers, conducting what should have been routine hydrographic mapping, had discovered a network of massive oceanic sinkholes, some exceeding 1,000 feet in diameter and plunging more than 800 feet into the seafloor, that were actively growing, interconnected, and showing signs of catastrophic geological instability. These weren't the familiar blue holes that divers explored in the Bahamas or the known karst features that had been mapped for decades. These were something new, something terrifying in their scale and behavior, something that suggested the very foundation beneath one of America's most populous states was beginning to collapse. Within hours, federal agencies descended on Florida. Satellite surveillance was redirected, and marine research vessels from across the Atlantic were racing toward coordinates that marked what scientists were calling the most significant marine geological event in modern American history. This is the story of how a routine scientific expedition uncovered a nightmare scenario that could reshape Florida's coastline and force millions to reconsider whether one of the nation's fastest-growing regions was built on ground far more fragile than anyone had imagined. The RV Atlantic Explorer, a research vessel operated by the Harbor Branch Oceanographic Institute at Florida Atlantic University, had been conducting standard hydrographic surveys of the continental shelf off southeastern Florida for 3 weeks, when the mapping data began showing anomalies that marine geologist Dr. Sarah Chen initially dismissed as equipment malfunction. The multi-beam sonar, which uses sound waves to create detailed maps of the seafloor, was displaying what appeared to be impossibly deep voids in areas that previous surveys had shown as typical shelf topography: gently sloping sandy bottom, dotted with the expected limestone outcrops and occasional coral formations. "We thought the transducers were miscalibrated," Dr. Chen would later tell investigators. "The depths we were recording didn't match any historical data, and the features were appearing in locations where we had reliable surveys from just 5 years ago. It seemed more likely that our equipment was malfunctioning than that the ocean floor had fundamentally changed in such a short period." But as the Atlantic Explorer made repeated passes over the same coordinates, using different sonar systems and cross-checking with satellite altimetry data, the impossible became undeniable. The ocean floor, approximately 15 miles off the coast of Fort Lauderdale, in waters between 200 and 300 feet deep, was pockmarked with massive circular depressions that hadn't existed in previous surveys. Some of these features measured over 1,000 feet in diameter, large enough to swallow multiple city blocks, and descended an additional 600 to 800 feet below the surrounding seafloor. The geometry of these features was what first suggested they weren't natural blue holes or typical karst formations. Blue holes, common in limestone regions like the Bahamas, form over millennia through gradual dissolution of carbonate rock by slightly acidic groundwater. They're typically circular, with relatively stable walls, and they develop predictably in areas where geological conditions favor their formation. The features Dr. Chen's team was observing showed different characteristics: near-perfect symmetry suggesting rapid formation, fresh sediment patterns indicating recent collapse, and most troublingly, evidence of active ongoing change. When the team deployed a remotely operated vehicle, ROV, to visually inspect one of the smaller features, the footage it returned was unlike anything in their collective experience. The walls of the depression weren't the gradual slopes of typical blue holes, but near vertical drops showing fresh scarring and active slumping. Sediment clouds hung in the water, indicating recent disturbance. Most unsettling were the acoustic anomalies, low-frequency sounds picked up by the ROV's hydrophones that suggested movement deep within the features, a rumbling that one technician compared to the sound of a building slowly collapsing in slow motion. Dr. Chen immediately contacted the United States Geological Survey, USGS, and the National Oceanic and Atmospheric Administration, NOAA, providing preliminary data and requesting assistance with what was clearly becoming a major geological investigation. Within 48 hours, additional research vessels were being diverted to the area, and federal scientists were reviewing decades of historical data trying to understand how such massive features could have appeared so suddenly in one of the most studied stretches of ocean in the world. As more vessels arrived and the survey area expanded, the true scale of the discovery became apparent and deeply alarming. The initial features off Fort Lauderdale weren't isolated anomalies, but part of a vast network of interconnected sinkholes stretching along Florida's southeastern coast from Palm Beach down to the northern Keys, a distance of roughly 80 miles. More than 40 major features had been identified within the first week of intensive surveying, with new discoveries being made daily as researchers expanded their search patterns. The largest of these oceanic sinkholes, designated FS1, Florida Sinkhole 1, in research documents, measured approximately 1,400 feet in diameter and descended more than 850 feet below the surrounding seafloor. To put this in perspective, FS1 could accommodate the Empire State Building laid on its side with room to spare. The volume of material that had apparently collapsed to create this single feature exceeded 30 million cubic meters, roughly equivalent to 12,000 Olympic-sized swimming pools of limestone, sand, and sediment that had simply vanished into the earth. But size alone wasn't what terrified the researchers. It was the evidence of active, ongoing collapse. Time series sonar imaging, conducted by running repeated surveys over the same areas at intervals of just hours, showed that the features were growing. FS1 expanded by approximately 15 feet in diameter during a 72-hour observation period. Smaller features showed even more dramatic changes, with some doubling in size within a week. Seismometers deployed on the seafloor detected constant low-magnitude tremors, the geological equivalent of a structure under stress, groaning as it approaches failure. The interconnected nature of the sinkhole network added another layer of concern. High-resolution side-scan sonar revealed tunnels and fractures connecting multiple features, suggesting that the collapses weren't independent events, but manifestations of a single, massive geological process occurring beneath a large swath of Florida's continental shelf. Geophysicists began constructing three-dimensional models of the subsurface, and what they revealed was nightmarish: an extensive network of voids and weakened zones extending inland toward the coast, following pathways in the limestone bedrock that formed the foundation of southeastern Florida. Dr. Marcus Rodriguez, a marine geologist from the University of Miami, brought in to help analyze the data, described the situation in terms that captured both the scientific and existential dimensions of the crisis. Imagine a house where termites have eaten away much of the wood framing, but the walls haven't collapsed yet because they're still supporting each other. That's essentially what we're looking at with Florida's continental shelf. The limestone foundation has been compromised over a vast area, and we're witnessing the beginning of a large-scale structural failure. The question isn't whether more will collapse, it's when and how much. The geological mechanism behind the collapses remained uncertain, but leading theories focused on Florida's unique subsurface structure. The entire state sits atop a thick platform of limestone and dolomite, porous carbonate rocks riddled with cavities, channels, and underground rivers carved over millions of years. This karst topography makes Florida uniquely vulnerable to sinkholes on land. The state experiences more sinkholes than any other in the nation, but the oceanic sinkholes represented something different and more menacing. Massive, rapid collapses occurring offshore, but potentially extending inland, following fractures and weaknesses in the limestone that could undermine coastal cities built atop the same unstable foundation. As the scope of the disaster became clear, research teams deployed increasingly sophisticated ROVs to explore the sinkholes' interiors, hoping to understand their structure and predict their behavior. What these robotic explorers discovered added new dimensions to an already alarming situation and raised questions that extended beyond geology into realms that seemed to belong more to science fiction than scientific investigation. The ROV Deep Surveyor, equipped with high-definition cameras, sampling equipment, and a comprehensive sensor suite, descended into FS1 on a mission that its operators would later describe as both scientifically crucial and deeply unsettling. The walls of the sinkhole showed clear stratigraphy, layers of limestone, sand, and fossil-bearing rock, but the layers were fractured and displaced in ways that suggested violent, rapid collapse rather than gradual subsidence. Massive boulders, some weighing hundreds of tons, had tumbled into the void and now rested at precarious angles against the walls. But it was at depth, where the sinkhole transitioned into what appeared to be natural cave systems, that the ROV encountered phenomena that defied easy explanation. The water temperature dropped dramatically from a surface temperature of approximately 78 degrees Fahrenheit to readings below 50 degrees at depth, far colder than expected given the depth and location. The temperature gradient suggested upwelling from much deeper sources, possibly connected to aquifer systems or even deeper geological structures. More disturbing were the acoustic readings. The ROV's hydrophones detected what researchers described as harmonic tremors, sustained, rhythmic vibrations similar to those detected near active volcanoes when magma moves through underground channels. But Florida has no volcanic activity, no magma chambers that could explain such signals. The sounds seemed to emanate from deeper within the cave systems, from passages that extended beyond the ROV's depth rating and disappeared into darkness that the vehicle's lights couldn't penetrate. Sediment samples collected from various depths within the sinkholes revealed another puzzle. Mixed among the expected limestone fragments and marine sediments were materials that appeared out of place, clays and minerals typically found much deeper in the geological column, suggesting that whatever process was causing the collapses was reaching down into ancient rock layers and bringing them to the surface. Some samples contained microfossils of species extinct for millions of years, now suddenly exposed to modern seawater after eons of burial. Dr. Jennifer Park, a geochemist analyzing the samples, noted anomalies in water chemistry that suggested active fluid circulation from deep sources. We're seeing elevated levels of methane, hydrogen sulfide, and other gases that indicate these sinkholes are connecting surface waters to much deeper systems, possibly tapping into confined aquifers or even deeper geological reservoirs. The implications for Florida's groundwater are potentially catastrophic. If seawater is infiltrating these deep systems, it could contaminate aquifers that millions of people depend on for drinking water. The ROV surveys also documented biological communities within the sinkholes that added ecological tragedy to the geological disaster. The abrupt seafloor collapses had destroyed coral reefs, seagrass beds, and other marine habitats that had taken decades or centuries to develop. Fish and invertebrates, disoriented by the sudden changes to their environment, were observed in abnormal abundances around the sinkhole edges, and dead zones, areas depleted of oxygen, were forming in some of the deeper features where decomposing organic matter consumed available oxygen faster than ocean currents could replenish it. The decision to partially shut down Florida's coast wasn't made lightly, and it reflected both the immediate dangers posed by the sinkholes and the unprecedented uncertainty about what might happen next. The federal response, coordinated between FEMA, NOAA, the USGS, and state emergency management agencies, represented one of the largest peacetime mobilizations of geological expertise and monitoring equipment in American history. The immediate shutdown focused on three priorities: evacuating people from potentially dangerous coastal zones, restricting marine traffic that might be at risk if seafloor collapses generated underwater landslides or localized tsunamis, and deploying monitoring equipment to track the sinkhole's evolution and provide early warning of major collapse events. Coastal evacuation orders were surgical rather than blanket, targeting areas where geological assessment suggested the highest risk of sinkhole propagation inland. Residents within a quarter-mile of the coast in sections of Fort Lauderdale, Hollywood, and Dania Beach, neighborhoods built on filled land atop limestone bedrock, received mandatory evacuation orders. The logistics were staggering. Temporary shelters had to be established, businesses shuttered, and critical infrastructure like hospitals and emergency services relocated or reinforced. The economic impact was immediate and severe, with preliminary estimates suggesting losses exceeding $2 billion per week that coastal areas remained closed. Marine traffic restrictions created chaos in one of the world's busiest shipping regions. Port Everglades, one of Florida's largest ports handling cruise ships, container traffic, and petroleum products, reduced operations to essential activities only. The Coast Guard established exclusion zones around the most active sinkhole clusters, forcing shipping lanes to be rerouted and adding days to voyage times for vessels that would normally transit close to shore. Cruise lines canceled Florida stops, sending ships to alternative Caribbean ports and leaving thousands of hospitality workers suddenly unemployed. The monitoring network established in response to the crisis was unprecedented in scope and sophistication. Arrays of ocean bottom seismometers were deployed across across hundreds of square miles, creating a network that could detect and locate even tiny tremors. Satellite radar was retasked to conduct continuous interferometric measurements of coastal land elevation, watching for any sign that the seafloor collapses were beginning to affect terrestrial areas. Tide gauges were monitored for anomalies that might indicate underwater landslides or seafloor displacement. And teams of geologists established 24/7 watch centers, where data from all these sources was synthesized, analyzed, and used to update risk assessments multiple times daily. Public reaction to the shutdown ranged from grateful acceptance of necessary precautions to angry denial that the threat was real. Conspiracy theories flourished online, with some claiming the sinkholes were being caused by secret government mining operations, others suggesting they were the result of underground nuclear tests, and still others seeing them as evidence of supernatural or extraterrestrial activity. The scientific community worked to combat misinformation, but the inherent uncertainty about what was causing the collapses and what might happen next made it difficult to provide the clear, definitive answers that a frightened public craved. Tourism, Florida's economic lifeblood, collapsed almost overnight. Hotels that should have been fully booked for spring break sat empty. Theme parks saw attendance drop by more than half as families canceled vacation plans, unwilling to visit a state where the ground itself seemed to be giving way. Real estate markets froze, with both buyers and sellers unsure how to value coastal property when the very land it sat on might literally disappear. Insurance companies began issuing force majeure clauses and refusing to write new policies, creating a spiral of economic uncertainty that threatened to outlast the physical crisis itself. To understand why Florida was experiencing such catastrophic seafloor collapses, geologists had to consider the state's unique and precarious geological situation. Florida is, in many ways, North America's most geologically unusual state, a low-lying platform of carbonate rock emerging only recently, in geological terms, from the sea, sitting atop older igneous and metamorphic basement rocks that form the stable core of the continent. The limestone and dolomite that form Florida's surface and shallow subsurface are products of millions of years of carbonate deposition in warm, shallow seas. These rocks are inherently porous and soluble, riddled with cavities, channels, and caves carved by slightly acidic groundwater percolating through the rock. This karst topography is beautiful. It creates the crystal-clear springs that are tourist attractions and ecological treasures, but it's also inherently unstable. The rock literally dissolves over time, and as it does, overlying material can collapse into the voids left behind. Florida experiences an average of several dozen significant sinkholes per year on land, events where the ground suddenly opens up and swallows homes, cars, or sections of highway. Most are relatively small, but some have been catastrophic. In 2013, a sinkhole in Seffner swallowed a bedroom of a house, along with the man sleeping in it, who was never recovered. In 1981, a sinkhole in Winter Park grew to 350 feet wide and 75 feet deep, consuming a house, several cars, and part of a municipal pool. These events, while dramatic, were understood and accepted as part of living in Florida. Rare, unpredictable, but manageable risks. What was happening offshore represented a different order of magnitude. The oceanic sinkholes weren't isolated collapses of small voids, but appeared to be manifestations of wholesale failure of large sections of the carbonate platform. Dr. Thomas Morrison, a geologist specializing in karst systems, explained the mechanism. Think of the limestone platform as a sponge that's been partially dissolved. Over time, groundwater flowing through it has created an interconnected network of cavities and weak zones. As sea level has risen over the past century, about 8 inches in southern Florida, the hydraulic pressure on these systems has changed. Add in the weight of coastal development, the pumping of groundwater that changes subsurface pressure relationships, and possibly seismic activity from distant earthquakes, and you create conditions where large-scale collapse becomes increasingly likely. Some researchers pointed to evidence of changing ocean chemistry as a contributing factor. As the ocean absorbs more carbon dioxide from the atmosphere, it becomes more acidic, a process called ocean acidification that's primarily concerning because of its effects on shell-forming organisms. But more acidic seawater also dissolves limestone more rapidly, potentially accelerating the weakening of carbonate rocks at the interface between the seafloor and the overlying water. While this process occurs slowly on human timescales, it could have reached a tipping point where structures weakened over decades suddenly failed catastrophically. Others noted the potential role of underground fluid extraction. Florida's population has grown exponentially over the past century, and with it, the demand for fresh water. The Floridan Aquifer, one of the most productive aquifer systems in the world, supplies water to millions of people and countless agricultural operations. Decades of pumping have lowered water levels in many areas, changing subsurface pressure relationships and potentially destabilizing rock formations that were previously supported by fluid pressure. Most concerning was the possibility that the collapses represented early stages of a much larger event. Geological evidence from Florida's past suggests that massive platform collapses have occurred before, leaving features visible in the bedrock topography. The Okeechobee Basin, a depression now largely filled by Lake Okeechobee, might represent an ancient collapse feature. If the current sinkholes were connected to a similar large-scale destabilization, the long-term implications were almost unthinkable. They suggested that major portions of Florida's limestone platform might be approaching structural failure, with consequences that could reshape the state's geography and force mass migration from coastal areas. By late May 2025, the nightmare scenario that geologists had feared began materializing. The first confirmed land-based sinkhole connected to the offshore collapses appeared in a Dania Beach neighborhood just 3 blocks from the ocean. The sinkhole, approximately 40 feet in diameter and 60 feet deep, opened beneath a residential street at 3:17 a.m., swallowing 2 parked cars and undermining the foundations of 3 houses that had to be evacuated and eventually demolished. Initial investigation suggested that the land-based collapse was indeed linked to the offshore features. Ground-penetrating radar and seismic surveys revealed a network of voids in the subsurface limestone extending from the beach inland, following pathways that appeared to connect with the Oceanic sinkhole system. The geometry suggested that as the offshore collapses removed support from adjacent rock, stress was being transferred inland, triggering secondary failures and a domino effect that could potentially reach several miles from the coast. Within a week, 2 more land-based sinkholes appeared in Fort Lauderdale and Hollywood, and geological surveys identified dozens of areas showing warning signs. Subsurface voids detected by radar, subtle ground settlement measured by precise GPS, and cracks appearing in roads and building foundations. The evacuation zone was expanded, now extending up to half a mile inland in some areas, displacing tens of thousands of additional residents and essentially creating a buffer zone of abandoned neighborhoods between the ocean and areas still considered safe for habitation. The psychological impact on Florida's population was profound. Residents of coastal areas, even those outside evacuation zones, reported anxiety, insomnia, and stress-related health issues. Children refused to sleep in their bedrooms, fearing the ground would open beneath them. Property owners faced impossible decisions: stay and risk catastrophic loss, or abandon homes and businesses that might never recover their value. The social fabric of coastal communities began tearing as some families left, while others, unable or unwilling to relocate, remained in increasingly empty neighborhoods that felt post-apocalyptic. The economic consequences rippled far beyond the directly affected areas. Florida's economy, heavily dependent on tourism, real estate, and service industries, contracted sharply. State tax revenues plummeted, creating budget crises that forced cuts to essential services. Insurance companies declared force majeure and refused to pay claims related to the sinkholes, arguing that the collapses constituted a geological catastrophe beyond the scope of standard policies. Legal battles erupted as property owners sued insurers, mortgage companies, and government agencies, seeking compensation or relief from debts on properties that were now uninhabitable or worthless. Marine ecosystems continued deteriorating as the sinkholes disrupted ocean floor habitats. Fisheries reported dramatically reduced catches as commercially important species abandoned areas affected by the collapses. Coral reefs, already stressed by warming ocean temperatures and disease, suffered additional mortality as sinkholes altered water chemistry and circulation patterns. Environmentalists warned that the ecological damage could take decades to recover, if recovery was even possible, given the continued geological instability. As the crisis extended through summer 2025, attention shifted from simply monitoring the disaster to exploring whether anything could be done to stabilize the situation and prevent further collapses. Engineers, geologists, and government officials debated options that ranged from ambitious engineering interventions to managed retreat from the coast. Some proposals focused on attempting to stabilize the limestone bedrock through grouting, injecting concrete or other materials into voids to fill them and prevent collapse. This technique had been used successfully for smaller sinkholes on land, but the scale required for the oceanic features was unprecedented and potentially impossible. Filling even a single feature like FS1 would require millions of cubic yards of material, and the interconnected nature of the voids meant that material injected in one location might simply flow through the network without providing meaningful support. The costs would be astronomical, potentially exceeding $1 trillion, with no guarantee of success. Other engineers proposed creating artificial reefs or other structures that might redistribute stress and prevent the spreading of collapses inland. But the dynamic nature of the situation, with new collapses appearing regularly and existing features continuing to grow, made it unclear where such structures should be placed or whether they would provide any real benefit. More radical proposals suggested accepting that parts of coastal Florida were becoming uninhabitable and focusing instead on managed retreat, systematically relocating people and infrastructure away from the coast, abandoning areas at highest risk, and establishing new defensive lines further inland. This approach had been used in response to coastal erosion and sea level rise in other parts of the world, but never at the scale that would be required in Florida, where millions of people lived in potentially affected areas. The federal government faced unprecedented decisions about disaster assistance and long-term planning. Should taxpayers fund the reconstruction of coastal areas that might simply collapse again? Should mortgage relief be provided to homeowners whose properties had lost all value through no fault of their own? Should the government buy out coastal property and create permanent buffer zones? Each option carried price tags in the hundreds of billions of dollars, and none offered clear paths to resolution. Meanwhile, research continued into understanding the root causes of the collapses, hoping that better understanding might suggest intervention strategies. Some scientists theorized that reducing groundwater extraction might help by allowing aquifer pressures to recover, potentially stabilizing the limestone. Others suggested that the collapses might be self-limiting. Once the most weakened areas had failed, the remaining rock might prove more stable. But these were hypotheses, not proven theories, and implementing policies based on them would be gambling with the futures of millions of Floridians. As 2025 progressed and the crisis showed no signs of resolution, Florida and the nation grappled with an uncomfortable truth. One of America's most populous and economically important states was built on a foundation that was literally crumbling beneath it. The oceanic sinkholes had revealed a vulnerability that couldn't be wished away or easily fixed. Florida's limestone platform was inherently unstable, subject to collapse processes that might continue for years or decades. Some coastal residents, tired of uncertainty and unable to maintain homes in evacuation zones, made the difficult decision to leave Florida entirely. Others retreated inland, creating demand surges for housing in central Florida cities like Orlando that drove up prices and created new infrastructure challenges. Still others remained in coastal areas despite the risks, unable to walk away from homes and communities they'd spent lifetimes building, choosing to gamble that their particular piece of ground would remain stable, even as others fell away. The crisis forced broader conversations about climate resilience and the wisdom of building in geologically unstable or environmentally vulnerable areas. Florida had already been grappling with rising sea levels, increasingly intense hurricanes, and sunny day flooding from high tides. The sinkholes added another dimension to an already challenging situation. Some urban planners and environmental scientists argued that the crisis was a wake-up call, demonstrating the need to fundamentally rethink how and where coastal development should occur. The oceanic sinkholes also raised troubling questions about whether similar conditions existed elsewhere. If Florida's carbonate platform was subject to such catastrophic collapses, what about the Bahamas, built on similar geology? What about the Yucatan Peninsula, or Pacific Island nations built on coral atolls and limestone? The discovery suggested that coastal karst regions worldwide might face similar vulnerabilities, potentially requiring massive reassessment of coastal development and new monitoring networks to provide early warning of geological instability. As the immediate panic of the initial discovery gave way to grim acceptance of a long-term crisis, Florida settled into an uneasy new normal. Parts of the coast remained closed. Evacuation zones were periodically adjusted based on the latest geological assessments, and residents lived with the knowledge that the ground beneath them was less solid than they had believed. The state that had represented opportunity, growth, and the American dream of tropical paradise had been forced to confront the reality that paradise was built on ground far more fragile than anyone had imagined, and that the bill for decades of development on unstable foundation was coming due in ways both terrible and terrifyingly uncertain.